In our last class, we had seen that the finite element method, this technique finite element method, what it does is it converts the infinite degrees of freedom of an object to a finite degrees of freedom by meshing it or by discretizing it into a predefined shapes called as elements, and it gives us solution nodes only at these nodes. So thereby changing these infinite points into finite points, and that is the one way of describing what this finite element method does. Let us try to understand what finite element method is in slightly different way. Here we have two equations. This is what is called as differential equation, and this is what is called as algebraic equations. This is what is called as algebraic equation. Now here this equation is given to you and it is specified in this region x goes from 0 to L, and these are something called as boundary conditions, and our objective here is to find what is u. So after solving this differential equation, I need to find what is u, and we have here on the right hand side, we have here the set of algebraic equations, and you need to find what is x and y from these equations. Here the equation is ax plus by equal to c and dx plus ey equal to g, and we need to find what is x and y. Now of course, given a choice to anyone, will always prefer to solve this kind of equations over this. This is very simple. We have been studying this through our school days, how to solve the simultaneous equations. Now, what finite element method exactly does is it converts this differential equation into set of linear algebraic equations. This is what exactly finite element method does. This is a method which converts this set of differential equations into the set of linear algebraic equations which are easy to be solved. And suppose this equation is more complicated, and then here the way we have got two equations, we might get 8, 10 or as many as equations, but this if this set of linear algebraic equation is very large, we can easily solve them by using computers. So finite element method is a technique which converts this differential equation into set of linear algebraic equation. Now why this is important? If you look at this equation carefully, this equation is the governing differential equation of a bar subjected to loading. A one-dimensional bar, a 1D bar subjected to loading. What this tells us that, or in general, we can say that any engineering problem can be modeled using differential equations. Any engineering problem in the nature can be modeled using differential equation. It may be an ordinary differential equation or it may be a partial differential equations, but any engineering problem can be modeled using differential equations. And then the nature of this differential equation is such that most of the differential equation, remember this word, most of this differential equation are not easy or cannot be solved by analytical method. Most of these equations cannot be solved using analytical methods. Cannot be solved using analytical method. Of course, this equation is not that difficult and we can solve it analytically, but most of the differential equations which results from the different engineering problems cannot be solved using analytical method. So the only way by which we can solve this differential equation is convert this differential equation into set of this linear algebraic equations by using some technique, and then solve these differential equations and find the result. And that is why in the process of converting this differential equation into the set of linear algebraic equation, we do the lot of approximation, and that is the reason the final results which we get from this technique of finite element method is not accurate but approximate, right? Now let us see how exactly we get this kind of equations. How exactly we get this kind of equations? What we'll do is we'll take we'll take same example. We'll take an example of axial deformation axial deformation of bar. In this example, we'll see how we end up getting differential equations from given problem. Suppose if we have a bar of say varying cross section a 1D bar of varying cross section in x direction of length say L, and subjected to suppose a distributed load and subjected to distributed load of qx. This x in the bracket tells you that this q or this distributed load varies with respect to x, and let it be subjected to a point load at the free end of this bar, and this is our direction of x, and also this area is changing with respect to x, and let the material property of this bar be E, which is Young's modulus. Now the first thing that you need to understand is we will be modeling this structure considering it is a one-dimensional structure. We'll be modeling the governing equation of this structure assuming that it is a one-dimensional structure. Now what are one-dimensional bodies or one-dimensional structure? If one, which we had already seen in our last lecture, that any structures whose one of the dimension is very large compared to the other two dimensions can be termed as one dimensional structure. Here its length is very large compared to its cross section, and that is why we'll model this problem assuming it is a one dimensional structure. All right, now what we'll do is we'll take a small element from this bar. We'll take the small element whose length we'll consider as dx, and then if I make it large here, so it will look somewhat like this. Fine, this is the length dx. This is the enlarged view of this small element dx. Now this element is subjected to forces in both the direction, and let that force, we'll call that force as some force small f, which is a function of x. As x is changing, this force is changing, and due to this length dx, the change in force on the right face will be f of x plus some change in force in x direction, and it is also subjected to a distributed force q of x. And then our sign convention here, and our sign conventions will be, we'll consider tension as positive. We'll consider this tension as positive and compression as negative. Then let me just again remind you that this q of x is body force and f of x are some forces on left and right face. Now, for this element to be in equilibrium, we know that the summation of forces in x direction should be equal to 0. And here, since this is one-dimensional problem, we are not worried about what will be the summation of forces in y direction. In fact, there won't be any forces in y direction because we have assumed it to be a one-dimensional problem. So whatever are the forces, it will be only in one direction, that is direction x. In that case, the forces which are acting in x directions are f of x is in the opposite direction, so that will be minus f of x. Then we have q of x multiplied by dx in the positive x direction. Now, since this is a distributed force, sorry, this was not the body force, this is the yeah, we can call it as body force also, but more appropriately it will be a distributed force. Fine. So minus f of x is this force because it is acting in the negative x direction, the direction opposite to the x direction. Then q of x is in the direction of x, and this, since this is a distributed force per unit length, we'll have to multiply it by the length, which will give us the actual force in positive x direction. Also, we have on this face a force f of x plus d f of x acting on this face, and the summation of all these forces should be equal to 0. This is nothing but summation of forces in x direction is equal to 0, or equilibrium equation. Now from this equation what we get is, this equation will give us df by dx will be equal to minus q. How do we get that? Minus f of x and plus f of x will be cancelled. I can keep this side, and this term, once it goes on the right hand side, it will become minus q of x dx, and then dx, if I bring it down, finally what I will get is df of x by dx equal to minus q of x. I'll keep this equation as it is. We'll call it as equation 1, and we'll keep it as it is. Now by Hooke's law, we already know that stress, if it is varying in the direction of x, is proportional to strain. The stress is proportional to strain, and that proportionality sign can be removed by using Young's modulus. We know by Hooke's law, we know that stress is proportional to strain in elastic limit, and if stress and strains are varying with respect to x, then it will be stress sigma of x, epsilon of x, and the proportionality sign can be removed by using a constant called as Young's modulus. Also the force and stress relation in terms of area is given as force is area times stress. We must be knowing it as P is sigma as force by area. But if forces and stresses and areas are changing with respect to x, then it will be f of x equal to a of x and sigma of x. Also by strain displacement relation, we also know that strain is given as du by dx. So these three equations, if you make use of these three equations in our equation 1, then if you make the use of these three equations in equation 1, see, we have here d by dx of f of x. So f of x, we have got it as a of x into sigma of x. In place in this equation I will substitute what is sigma of x. So this I will substitute it here. So f of x will be E epsilon of x sigma of x. And then further epsilon, what is epsilon x? Epsilon x is this, right? So finally epsilon x will be du by dx, and then sigma x will be E du by dx. So f of x from this equation we will get it as E times a of x, E times a of x multiplied by strain, that is du by dx, and this should be equal to minus q of x, wherein q of x is the distributed load. So if I bring this on the left hand side, the final equation which we get is EA d square u by dx square plus q of x is equal to 0, and this is nothing but the governing differential equation of a bar which is subjected to the distributed force, and x, where x varies from 0 to n. So the purpose of this derivation is just to show that any engineering problem can be modeled by differential equation, and these kind of equations are called as governing differential equations. Of course, we cannot solve this problem unless and until we use something called as boundary conditions. Here the boundary condition is, since it is fixed on this end at x equal to 0, since it is fixed, the displacement at this point where x equal to 0 will be 0, since it is fixed. So our first boundary condition will be boundary conditions at x equal to 0, the displacement will be 0, and at x equal to L, let us see what happens at x equal to L. At x equal to 0, this is fixed, but at x equal to L, there is one point load, or a point load which is equal to F is applied at x equal to L. Fine. Now here we have a general expression for force. This is the expression for force, right? Because we had the equation d f of x by dx. So f of x we have replaced by this. So this is the expression for force. But at any value of x, this expression is at any value of x. But we have here a specific case wherein at x equal to L, that means all the x will replace it by L. At x equal to L, this force becomes equal to F. Now these are the two boundary conditions which are required to solve this differential equation in this region. Now these two types of boundary conditions are different in nature. This boundary condition has to do with where this bar is constrained, or this boundary condition has to do with the displacement, and that is why this kind of boundary conditions are called as essential boundary condition. This is an important concept. This boundary condition is called as essential boundary condition, and this boundary condition has to do something with the applied force or the moments, and that is why this kind of boundary conditions are called as natural boundary conditions. This is essential boundary conditions, and this type of boundary conditions are called as natural boundary conditions. Again, essential boundary condition has to do something with the displacement or the constraints, and then the natural boundary condition has to do something with that of applied forces or applied loads. Again, now you might wonder why we have taken boundaries only this and not this, because since we have treated this as the one-dimensional problem, we are not really bothered about what happens across these boundaries, since we are only interested in its one dimension. For us, the boundaries which matter is only this and this at x equal to 0 and at x equal to L. So at both the boundaries, we have these boundary conditions. Now, the type of this type of differential equations which requires boundary conditions to obtain the solution are called as boundary value problems. Again, I'll repeat, the boundary conditions which requires, the differential equations which require boundary conditions to obtain its solutions are called as boundary value problem. All right. So to conclude, we have seen that a finite element method is a tool which converts its differential equation into set of linear algebraic equations, and then any problem can be modeled using differential equations. For example, here we have seen the bar can be modeled using the differential equation Ea d square u by dx square plus qx equal to 0. This is called as governing differential equation. Governing differential equation. And the problems, the differential equations which requires boundary conditions, to obtain its solution are called as boundary value problems.